Okay, I think we continue. So, after the introduction, we shall look now at partial differential equations. So in fluid flow, heat transfer, structural mechanics, electromagnetics and other fields, the physical phenomena occurring are governed by PDEs. The example that is relevant to us when we want to do computational fluid dynamics, that are the Navier-Stokes equations. And I want to limit here to incompressible flow. And moreover, with constant viscosity. And as you know from your fluid mechanics course, you can write this is topic 1a, in the following form. We have the time derivative of the velocity vector v plus, and then we have the vective term, which we can write as velocity vector v dot product with the nabla operator, and that is operating on the velocity. So that's a nonlinear term, because we have here a combination of the unknown velocity and derivatives of the velocity. As soon as we have this, we have a nonlinear term. On the right hand side, we have, if you see, I divide it by the density, which we assume to be constant in this case, so that is rho. And then we have on the right hand side the gradient of pressure. We have nu, the kinematic viscosity, times the nabla squared, or the Laplace operator, giving us second derivatives of the velocity. And we have, if we have gravity or any other external forces, we have, in that case, we call it G. So that would be then the set of equations that we call the Navier-Stokes equations. In CFD, we also include the continuity equation. So that would be the 1D, that we have the divergence of the velocity is equal to 0. So that is usually, this set of equations is referred to as the incompressible Navier-Stokes equations. So to tell you, well, you know, but I say it anyway, t is the time, and the nabla operator in Cartesian coordinates is the d dx, d dy, and d dz. So that is the nabla operator. V is the velocity vector. In Cartesian coordinates, we have the components u, v, and w. P is pressure. Rho is density. That is assumed constant here for incompressible flow. And the nu that is appearing, that is the kinematic viscosity, that is the viscosity, the dynamic viscosity divided by rho, that is called the kinematic viscosity. and G is the gravitational acceleration. If we had other external forces, then it would be the acceleration for those. For those of you who want to refresh, just look back at your textbook, which probably has been Chengal-Chimbala or White, Fluid Mechanics. So, that is the goal. But in our course, we want to look at model equations. And there are good reasons for that, because we want to focus on certain aspects in this and study also the numerical methods for that. And the model equations have the advantage that we can focus on these special aspects and that we usually have exact solutions for that. So we can check the numerical methods for these solutions. So we can compute the error and see which method is good, bad, how do they behave. And that is the idea. So we study that, we pick out these model equations, and in the end we can put it together and be able to solve that. So that will bring us then to the aspect of the model equations. So there we can say now quite a lot, but I want to limit that because we will later on discuss this in more detail. But imagine that we have a problem where everything is unimportant and the only thing important would be the change of velocity with respect to the gravitational acceleration. So if we have this situation, so that is if only we call that the source term, because that has no derivative in it, that is, in that case it is G, if that is only affecting the change of the velocity, then we get from the Navier-Stokes equations, and that is for the momentum equation, that will be from 1a, we get, I call this now equation 2, it would be dv, actually you can take it as a standard derivative, dv dt is equal to g. So, and that is an ODE. That is an ODE. That means an ordinary differential equation. The right-hand side is really simple in that case. In the general case, an ODE would be of the kind, say usually we could write it as dy of t, dt, is equal to a right-hand side depending on t and y. So y is the unknown. In our case, it would be the velocity vector v, and f in that case would even be independent of time and the solution itself. So it's a very simple problem, we could solve it directly. But imagine this would be more complex. If we had external forces that are varying in time, then we would have something similar to that. So therefore, that it will be interesting also from this aspect to look also at the numerical solution of ODEs, ordinary differential equations. And we will come back in the end, as we shall see also when we look at the full equation. So that is one aspect. Now we will continue in simplifying and getting this, the Navier-Stokes equation, the momentum equation. Now imagine that the pressure term, force generated by the pressure, and the external force are unimportant. Then the rest is left, and that can be simplified if we just look in one dimension. So, if minus 1 over rho times the gradient of the pressure plus the external acceleration is 0, and the problem is 1D, that is one-dimensional, then equation 1a becomes, let's look at that. So this is gone, and then if we are just in one dimension, we just have, say, the first component is u. So then we get equation 3, we get the time derivative of temperature, of the velocity component u, and here we get just u times ddx of u. So u times du dx, and on the right hand side, if this is gone, we just get from this the second derivative of u with respect to x. We get mu d squared u dx squared. And this is the 1D Burgers equation. Just the Burgers equation. After the Dutch scientist Burgers. And that is modeling nonlinear waves with diffusion. We should study that because it is a nice example to study nonlinear effects. And that's very relevant for discretization also of the incompressible, but even more of the compressible. Euler and Navier-Stokes equations. If we have nu equal to 0, then we have no diffusion, and then we have just the modeling nonlinear waves. Another aspect is if we linearize this equation. Let's now say that if the Burgers equation, that is 3, is linearized, and that means that u du dx, which is the nonlinear term, is replaced, or approximated as we like it, by a constant velocity a, the transport velocity, transport speed a, times du dx. Then we get from the Burgers equation, it might be difficult to see that, so we'll look over here. So that's the only thing. So if u du dx is replaced by a du dx. So I write it again because it's hard to see. U du dx is replaced by a du dx, where a is a constant advection speed. Is a constant advection speed. Then we have made the problem linear. That's much easier. So then we get the convection diffusion equation, the 1D convection diffusion equation. And that is the following then. We have still the time derivative of velocity, but now we have the linear term, which is just constant a times du dx. On the right hand side we have still kinematic viscosity nu, second derivative of u with respect to x. And that is modeling linear waves with diffusion. And if we continue on that, and we say, let's look at the case when the viscosity is 0, then we just are modeling linear waves. Then we get the so-called linear advection equation, which is the basic equation for hyperbolic problems. So then we have already seen now a couple. Now we continue. We now continue from the convection diffusion equation, and we assume that the advection speed is 0. We get the diffusion equation, which you already know. Which is u dt is equal to nu d squared u dx squared. And that is modeling viscous diffusion. If we replace u by T, the temperature, we can model heat conduction. So for U equal to temperature, find models heat conduction. And that is the typical example of a parabolic problem, as we shall see. So, still, if we go back to the original momentum equation of the Navier-Stokes equation, and we consider the case that the left-hand side, modeling the transport, is not important, that the pressure is not important, only this part is important. So, if viscous effects and the source term, which is the G here, are dominant, we get from 1a following equation, that is, when we get this, so the rest is 0, and if we divide by nu, then we get the nabla squared of the velocity. And now we just look at one component to make things easier. Say the x component u is then equal to some right-hand side, and that would be in 2D. That would be, we get from, let me add that, in 2 dimensions. That is indicated by that. Where in this example, the f would be, as we see from the equation, minus the x component of the gravitational acceleration divided by the kinematic viscosity. And what is this? This is the Poisson equation. is the Poisson equation, which is modeling the velocity distribution in very viscous flow. Again, if we had, instead of U, we had the temperature, we would have a heat transfer problem. And the F would be the heat sources. So we can interpret it in different ways. And we will also see it, actually it's beyond the course, but we can say it, and it was also, you mentioned radar, we have to solve this kind of equation for the incompressible Navier-Stokes equations. And then U is the pressure. So the pressure is governed by a Poisson equation. So that is the classical example for an elliptic equation. And then the set of equations that we cannot directly derive from this equation, where we actually need the compressible, actually the Euler equations. Euler equations is when the viscosity is 0. That is the wave equation. So, if viscous effects are negligible, let's see. That's right. That means we can ignore viscous effects. That means concretely in the equation that we can set the mu equal to 0. And linearizing, in that case it is a compressible Euler equation. We assume we have some stagnant flow where velocity is 0, constant pressure, constant density, and we assume we have small perturbations on that. Velocity, pressure, and in density. Then we get the 1D heat equation. If we restrict ourselves to 1D, we get in one dimension the 1D wave equation. And that is, we have in that case, the equation that we get from it, in the first place, is a system of equations. And we can reformulate it such that we get this equation, the second derivative of u with respect to time is equal to, and now we have the speed of sound c appearing on the right hand side, d squared u dx squared, where c is the speed of sound. That is of this uniform flow around which we have done the linearization. And that is modeling, this equation is modeling acoustic waves. So we could also model with it electromagnetic or elastic waves, just the same. Just the speed is then corresponding to the problem. And that is a typical example of a hyperbolic equation. So you see now we can simplify in various aspects and we get them these model equations. Now before doing the classification, what I already mentioned, hyperbolic, parabolic, elliptic, I would like to give you a physical classification. model equations, we look at the physical classification. First type of problems that we have there are equilibrium problems. And the example is the steady 2D heat equation. That is then following, equation 2.1. We have the second derivative of the temperature with respect to x, and we add the second derivative of temperature with respect to y. And that is equal to 0. We assume that we solve this in the unit square. So we have here 1, here 0. And so that is our domain. We call this omega. The boundary is called d omega. This is a little bit mathematical. Sometimes it simplifies things. And in the example in the textbook, we have on the left-hand side, at the boundary on the y-axis, temperature 0, and also on the right-hand side, temperature 0, and also at the upper boundary, temperature 0. And below we have some temperature that is larger than 0. How will then temperature develop inside omega? And it turns out that the problem is completely defined by the boundary conditions. So the boundary conditions determine what is going on. And if we change the boundary conditions at any point, we'll change the whole solution. So everything is dependent on the boundary condition. So that means in this example that we have here, the boundary temperature, or the temperature at the boundary, determines the temperature in the domain, which we call omega. So the solution will be in equilibrium with its boundary conditions. That's the name equilibrium problem. Another name of this is jury problem. Around we have the jury, the boundary conditions, and they say what is happening. They evaluate, they determine everything. So that is then is an equilibrium or jury problem. Because the temperature is in equilibrium with the boundary conditions and the boundary conditions of the jury of the whole problem. And changing the boundary conditions will change the whole solution in omega. If we would be able, at a point P in the domain, to change the solution there, we would say have a source suddenly there, put it in a source, then we would have something here. That would affect the whole solution. So then we would have the whole solution, if we would change something here, the whole solution in the whole domain would be affected. And that we can call then, if we have this situation, we would have then the domain of influence the point P. So that means if change the property, in that case, say, would add a source here at this point, it would affect all solution in the whole domain. And that has important consequences also for the numerical solution. Everything is coupled with each other. So if you have this to solve this problem in a coupled way, everything is connected to each other. We can have a problem like this, where the temperature is given, that is called the Dirichlet problem. Or we can give partial derivatives, usually the normal derivative at the boundary, that is called the Neumann problem. So, Dirichlet condition, if the dependent variable in that case, in our case, would be t, is given as, I think this uses acronym BC as boundary condition. And we would have a Neumann condition. Okay. Going back to John von Neumann, also one of the pioneers of CFD. If the normal derivative, so the TDN normal derivative with respect to the normal at the boundary, is given as boundary condition. And we can also have another condition called Robin condition. If a linear combination of Dirichlet and Neumann condition is given, so if say A1 T plus A2 the TDN is given as boundary condition. So that's also possible. In any case, this kind of problem, equilibrium or jury problems, are governed by elliptic PDEs. So this is an example. This is the Laplace equation. You would have here something on the right-hand side. Even would have a Poisson equation. See, there is no derivative in time appearing for this example, for the equilibrium problems. Only second derivatives. It's always the highest derivative that determine the order, by the way. But now, in the second type of problems, which are marching problems, we have in general some marching direction, which is usually time. So those are problems changing in the marching direction. It's kept general because in supersonic flow we can also be hyperbolic in the flow direction, the x direction. So then that would be the marching direction. But in general, this marching direction is time. We have two types. Type 1, this is hyperbolic problems. The example, that is 2.2, is the 1D wave equation. And that is, as we saw, second derivative of u with respect to time is equal to the speed of sound c squared times the second derivative of u with respect to x. And here we have to assume some knowledge. If you look at the textbook, you'll see the derivation of that. We don't want to do that here, we just want to give the result. Here we have the initial time, and we assume that we have some initial condition given there. And then we progress in time, and we ask ourselves, what is happening at a point x0 and a time instant t0? By which conditions is the solution at this point determined? It turns out it is determined by the so-called characteristics which go through this point. These are special curves which have special properties that are important that we shall look later on. In that case, the characteristics have more or less like this, so it should go through this point here. And I call this one here the x2 of t, and this one the x1 of t. So these are lines or curves in the xt plane. The x-coordinate is no longer an independent variable, it's dependent on time. And it's determined by the slope dx2 of t dt is equal to c, speed of sound, and this one here, the dx1 of t dt, is determined by minus the speed of sound. And although it doesn't look like that, but we can correct a little bit for that, it should be the same distance here and here. Because the distance here is the distance that the speed of sound has traveled in the time t0. So this distance here is the c times t0, traveled to the right, and from here it has traveled to the left. That is again c t0. So that means this point here, that is the point x0 plus c t0, and this one is the point x0 minus c t0. And if we look at the solution to this problem, we see the solution here is determined only by the initial condition in this interval. Only there. If we do anything here, it will have no effect on this point. If we do anything here, it will have no effect. We can only affect the solution in this region. That is called then the domain of dependence. So the domain of dependence of the wave equation at point P, which is say now is x0, t0, is the interval. As we saw here, that is x0 minus ct0 and x0 plus ct0. So that is then called the domain of dependence. And these lines that we have seen here, they are called characteristics. is x1 of t and x2 of t. So they have these properties, and you see they are linked in a way to the equation, because they are, the slopes is given by the speed of sound it's appearing here. What is the domain of influence? That means where, if we change the solution here, would again add a source term, whatever, where will we affect things? We will only affect here, between the characteristics, only in this part it will be effect. It will have no effect here, no effect in the past, nothing, only in this part in the future. So that is then the domain of influence of the point P. So if we say this is the point P x0, domain of influence. So you see a completely different behavior, limited to the region between the characteristics going through the point. And that is then an example of a hyperbolic PDE. So we have here initial conditions. We could also have boundary conditions, and we shall see that then also these characteristics play an important role to determine where boundary conditions should be given and where not. So then we can say that we have the example 2.2. That is an example of a transport problem. And that is governed by hyperbolic PDEs. So that is then this one. And the last one that I just mentioned, that is parabolic PDEs, where we have, for example, the heat equation, and in that case we have a situation of x and t, and we are, say, here as a point x1 and t1. We have the boundary here. Say this is 0, this is 1 times 0. Then the initial condition, or if we do anything here, we want to know what is affecting the solution at the time t1, then it will be affected by the complete initial condition, and we need boundary conditions here. So we need a boundary condition here. We need to specify, for example, t is equal to t0 here. As an example, t0 here. This is greater 0. We could give an initial condition here, 0. Then everything is determined by the boundary conditions up to this point and the initial condition. If we have this point here, it will influence everything in the domain from that point on. Everything in the future. So that is the domain of influence of this point P here in this example. And the equation that we have here, that is 2.3, would be the heat equation. dt the time is equal to alpha e squared t dx squared, where alpha is the thermal diffusivity. So that is an example of a parabolic PDE. then we have all the three types here. And by this brief characterization, you see, and what is it modeling? It's modeling diffusion. So this parabolic PDEs is modeling diffusion. In that case, it is the diffusion of heat, that is heat conduction. Okay, so then we have seen a brief review of the PDEs, giving the classification in terms of physical terms of what is it dependent and what is it influencing. Domain of influence, domain of dependence, and domain of influence. Okay, so tomorrow we'll look into the mathematical classification of second order PDEs. We have all the examples seen now here in this part. And we look at the sources of errors, which will be then the basis for assignment 1. And last but not least, please spread the news that there is a new interesting course, so that we get even more. There's still space for further students. Okay, see you then tomorrow morning.